Welcome to the deep dive.
And today, we're plunging into a concept that, honestly, might just fundamentally change how you think about problem solving.
Yeah, it's this idea of the curved geometry of problem spaces. Sounds a bit theoretical, maybe?
It can sound that way, but it has really practical implications.
Imagine for a moment you're deep into a complex logic puzzle, something really intricate, like,
Those ones that take hours.
exactly. You're meticulously piecing together clues, dedicating hours of thought and effort until you finally hit that glorious aha moment and the entire solution just clicks into place. It's a truly satisfying feeling, isn't it?
Oh, absolutely. One of the best feelings.
Now, here's the interesting twist. What if, immediately after solving it, you tried to undo your steps? Not just reverse the outcome, but literally retrace every mental deduction, every transformation of information, to return to the exact starting point of the puzzle without any extra effort, without any loss of clarity or information. Like, you could just perfectly rewind time.
Yeah, you'd find pretty quickly it's not that simple.
Right. The path you took to solve it often feels inherently different from any path you might take to unsolve it.
And what's truly fascinating here is that problem solving isn't always a flat, perfectly reversible journey. Like walking forwards and then simply turning around and walking backwards along the same exact steps.
Okay.
More often than not, when you're faced with a difficult problem, you instinctively transform it. You map it to a different, perhaps seemingly easier problem domain where you have more readily available tools or algorithms.
Right, you change its form somehow.
Exactly. Then you solve it there, in that new domain, and finally, you transform that solution back to the original problem space. And you'd intuitively think this kind of round trip should leave you exactly where you started, perfectly canceling out the initial transformation.
Like walking a perfect triangle on a flat map. You just end up back at the start.
Precisely. It feels like it should be a perfect loop.
But here's where it gets really interesting, and where our intuition often leads us astray. In reality, that journey rarely, if ever, perfectly cancels out.
Almost never.
You almost always expend some extra effort, maybe you lose a bit of clarity, or you introduce subtle approximations along the way. So the big question is, why? Why does this round trip often result in a net loss or an altered state?
And our sources suggest it's because the space of problems isn't flat, it's curved, much like the surface of a sphere or some other non-Euclidean geometry.
Curved. All right.
Indeed. So our deep dive mission today is to explore this profound concept of the curved geometry of problem solving.
Yeah.
We'll unpack precisely how this inherent curvature shows up in practical problem solving.
Okay.
Why it leads to what we call lossy transformations, and crucially, how our own human insight and prior knowledge don't just passively observe this space, but actively act like a gravitational lens, bending this problem space to our advantage.
Think about it. When you're faced with a big, messy, daunting problem, what's one of the first things you do? You try to break it down, right?
Yeah.
Or you transform it into something that feels more manageable, something you already have a method for.
Yeah, you look for an angle, a different way in.
Exactly. This core concept, this fundamental strategy is what we call problem reduction.
That's absolutely right. At its core, reduction means taking a difficult problem, which we can label as problem P, and mapping it, translating it to a different problem, problem Q.
Okay.
And this problem Q is typically one for which we already have known tools, algorithms, or even just familiar mental frameworks that are more readily available and efficient. It's really about converting an unfamiliar challenge into a familiar one, often just by changing its representation.
To make this really concrete, let's unpack it with an example almost everyone can relate to. Sudoku.
Ah, good one.
We all know it as a logic puzzle, our original problem P. You're given a grid, and your task is to deduce the correct numbers for empty cells based on a set of logical constraints. Each row, each column, and each 3x3 subgrid must contain all digits from 1 to 9 without repetition.
Right, pure logic.
It's intuitive, it's a bit like a mental workout, and it appeals to our human capacity for logical deduction.
Now, what's fascinating is that you could take that exact same Sudoku puzzle, that problem P, and represent it in a completely different domain as a network problem, which we'll call problem Q.
A network problem, how does that work?
Well, imagine each empty cell in the Sudoku grid becomes a node in a vast graph.
Okay.
If two cells are in the same row, column, or 3x3 square, meaning they can't have the same number, they are connected by an edge in this graph.
I see. The constraints become connections.
Precisely. The task then transforms from deducing numbers to coloring these nodes such that no two adjacent nodes, no two connected cells share the same color. For Sudoku, you'd be using 9 different colors, the digits 1 to 9.
So it's not a logic puzzle anymore, it's a graph coloring problem.
Exactly. A different mathematical domain entirely, with its own suite of algorithms and solution methods.
And then you can take that network problem, problem Q, and convert it even further into an optimization task, problem R.
You can. This might involve setting it up as a linear programming problem or maybe a satisfiability problem, where you're trying to find a configuration that minimizes the number of conflicts.
Or maximizes valid placements.
Right. You assign variables, set up equations based on the constraints, and let an optimization solver churn through it. So you've gone from an intuitive logic puzzle, P, to a visual network problem, Q, to an abstract mathematical optimization task.
That's quite a journey.
And the cycle doesn't end there. Once the optimization solver provides you with a solution for R, you then map that solution back to the network problem Q. From there, you translate it back to your original Sudoku grid, problem P.
Right. Get the numbers back in the grid.
On the surface, this entire process, P to Q to R, and then R back to Q back to P, sounds like a perfectly clean, efficient, and perfectly reversible round trip.
Yeah, it seems like it should be. As if you've traveled a perfect triangular path and landed precisely where you started without any discernible change, doesn't it?
It really does. It gives the impression of a perfectly clean, elegant loop, almost like flipping a switch on and then off.
But here's the crucial catch, the point where things get, well, lossy. There's almost always a net loss in that cycle. It's far from a free ride. It reminds me of those lossless claims for audio compression formats. Usually there's some loss, even if it's imperceptible.
That's a great analogy. First, there's an unavoidable loss of time. Each transformation, both encoding the initial data into the new problem type.
Like building the graph from the Sudoku grid.
Exactly. And decoding the results back, turning the graph coloring into the final Sudoku numbers, adds computational overhead. Think of it as paying a toll every time you enter a new city in our problem-solving journey.
Right. These conversions aren't instantaneous or free?
No, they consume CPU cycles, memory, wall clock time. Even what seems like a simple data reformatting operation can be surprisingly expensive when dealing with large-scale problems.
And this often comes with the loss of information too, right? Approximations creep in.
They certainly can. For instance, the original Sudoku puzzle strictly deals with discrete whole numbers from 1 to 9. But when you transform it into an optimization problem, maybe using linear programming, that solver might introduce fractional solutions or continuous variables.
So not neat whole numbers anymore.
Right. When you try to translate those back to the original Sudoku, you have to round them or make additional arbitrary choices, potentially losing precision that was inherent in the original problem's elegant logic.
Or, like you said, converting a detailed image to a line drawing, you lose texture.
Exactly the same principle. And finally, a particularly insidious one for us human problem solvers, a profound loss of clarity.
How so?
The original intuitive structure of the logic puzzle, the satisfying visual patterns of Sudoku can get completely buried under layers of mathematical abstraction.
Right, it's just equations now.
The elegant simplicity that made Sudoku solvable by hand might be entirely lost in the complex equations of a linear program or the intricate connections of a graph. When you finally get the answer back, it might be correct, but the journey to it was convoluted.
And the connection to the original problem's spirit, its structure, is gone.
Exactly. This makes debugging, explaining, or even learning from the solution far more difficult than if you had solved it directly using logic.
So this net loss, this extra time, the approximations, the blurred clarity isn't just an annoying side effect or a bug in our method.
No, absolutely not. It's not a saw of poor design.
It's fundamental.
It's a fundamental feature of how problems are connected in what we call a non-Euclidean space. To truly grasp this, we can draw a powerful analogy from differential geometry, which is the branch of mathematics that describes curved spaces.
Okay, geometry time. On a flat piece of paper, what we call a Euclidean space, if you draw a triangle and walk its perimeter, measuring the distances along each side.
Right, like in school geometry.
Those distances add up predictably, and you will, without fail, end up exactly where you started. The Gaussian curvature in such a flat space is 0. Everything is perfectly predictable, reversible, no surprises.
It's a nice, straightforward world where geometry behaves exactly as you'd expect.
But now, imagine attempting to walk that same triangle on the surface of the Earth.
Which is curved, obviously.
Right. If you set out on what seem like straight paths, what are mathematically known as great circles, the shortest paths between 2 points on a sphere, you won't necessarily end up precisely where you started if you simply sum the individual leg lengths as if the map were flat.
The paths bend due to the Earth's curvature, and the angles of your triangle will sum to more than 180 degrees.
Which is impossible on a flat plane.
Exactly. It shows that triangles don't close neatly. This inherent curvature of the Earth's surface measures how much these paths deviate from straight lines.
And applied to problems.
It quantifies the inherent inefficiency or loss of looping through these transformations.
Yeah.
It's not just an analogy. It's a profound mathematical parallel that explains why certain computational journeys have these unexpected costs.
That's a powerful visualization. So we're talking about a kind of fundamental twist in the very fabric of how problems relate to each other. And you're saying we can actually formalize and measure this curvature, give it a number.
Precisely. To make this concept mathematically rigorous, we borrow directly from metric geometry. We define a precise distance between problems, denoted as dA to B.
Okay, a distance.
And this represents the cost of reducing problem A to problem B. But this cost isn't just about the elapsed wall clock time on a computer. It's a much richer concept.
What else can it be?
It can encompass computational complexity, the number of operations required, maybe circuit distortion, how much a signal changes when converted, reduction overhead, the storage or processing needed just for the transformation itself, or what we call information distance.
Information distance.
Yeah, how much new information needs to be encoded or re-encoded when transforming one problem's representation to another, how much structural change happens.
So it's a measurable expense for changing the problem's form or representation. And these distances aren't just theoretical. You mentioned they can actually be calibrated. How would you do that in practice?
Yes, they can be. For example, in a research setting, you might run empirical experiments. You could build a software system that performs the A to B transformation, measure the average computational resources time, memory it consumes over many runs.
And that gives you a practical number.
Right. It gives you a practical calibration for dA to B. Or you could quantify the number of bits required to encode the transformation, or the error rate introduced. It's about assigning numerical values to the effort and potential loss incurred during transformation, grounded in real-world data.
Okay, that makes sense.
With that in mind, we can then define a curvature metric, which we denote by the Greek letter kappa, kappa PQR.
So what does the value of kappa tell us?
If kappa equals 0, this signifies that the problem space is flat, or Euclidean, for that particular triangular loop. The actual round-trip cost perfectly matches the sum of the individual transformation costs.
Perfect reversibility, no hidden costs.
Exactly. You truly end up where you started in precisely the same way, if kappa neck and x here. This is where it gets interesting. A non-zero kappa is like a fingerprint of hidden complexity. It signifies that the sequence of direct transformations, when looped, cannot perfectly undo itself without some irreversible cost, or perhaps an unexpected path emerges. It tells us that the simple sum of independent steps doesn't equal the cost of the entire cyclical journey, indicating a non-Euclidean geometry.
So a non-zero kappa proves the space is curved for that loop.
Correct. Let's delve into a specific, powerful example from our sources, often referred to as the perfect computational triangle. Imagine 3 conceptual cities of abstract problems, each representing a distinct class of computational challenges.
Okay, cities S, C, and V.
Right. City S represents logic puzzles, like assigning true-false values in Boolean logic, or solving constraint satisfaction problems. Think rigorous deduction. City C represents network problems, involving exploring connections, graphs, shortest paths, social networks, optimizing flows, all about relationships and structure. City V represents optimization tasks, selecting the best combination of elements under constraints, linear programming, training machine learning models, finding optimal states.
And we're interested in the roads connecting these cities, traveling from city S to city C, then C to V, and finally V back to S. And these roads have measured costs.
Yes, based on careful calibration from research studies, the costs or distances for these specific transformations have been measured empirically. The road from S logic to C network has a cost of approximately 1.094. The road from C network to V optimization costs about 0.742, and the road from V optimization back to S logic costs approximately 1.103.
Okay, got the numbers.
Now, if this computational problem space were perfectly flat, if its geometry were Euclidean, the expected sum of these individual legs for a full round trip would simply be 1.094 plus 0.742 plus 1.103.
Let me add that up. That's 2.939.
Exactly, 2.939. This is our baseline, the cost we'd expect in a flatland scenario where everything adds up nicely.
But here's the kicker, right? The point where the rubber meets the curved road.
Right.
When the full loop, SE or VS, is actually traversed and measured in a computational system,
Yes.
the real observed cost is found to be approximately 2.206.
Wow. Yeah, that's a significant difference from the 2.939 we expected.
It's almost 25% less. That seems odd, less costly.
It does seem odd at first. But let's calculate kappa using our formula. Kappa in text 7.93 cost, text 2.733.
So we have a positive kappa here, 0.733. What does that positive non-zero kappa specifically tell us? It's not zero, so it's curved. But why is it positive? Does that mean the loop is somehow more efficient than the sum of its parts?
That's the tricky part to interpret. The fact that kappa is non-zero, specifically positive in this calculation, confirms the triangle is curved. A positive kappa here means that the sum of the individual transformation costs, if you just added them up, was greater than the actual cost of completing the full round trip.
So it looks like a shortcut.
It looks like a shortcut, but the crucial takeaway isn't about getting a free lunch for nothing. It's that you don't end up where you started in exactly the same way. It signifies an inherent twist or an unexpected non-additive property in the map.
Ah, okay. The state changes, or information is lost or gained in a way that affects the overall cost.
Precisely. This twist reveals that these transformations are not perfectly reversible, and there's a fundamental difference in traversing the loop versus simply summing its individual legs. It implies that no single master solver can effortlessly convert between these problem types bidirectionally without incurring some form of extra cost or fundamentally changing the nature of the information.
So the positive curvature highlights that the whole cycle behaves differently than just adding up isolated steps.
Exactly. It suggests inherent inefficiencies or nonlinearities in the problem space itself. It's a powerful testament to the idea that the whole is sometimes less, in terms of measured costs in this case, but perhaps more complex in other ways, than the sum of its parts when navigating curved spaces.
That makes profound sense. It's not just about costs, it's about the very nature of the path. This sectional curvature concept in Riemannian geometry you mentioned earlier, that sounds like it's designed to capture these hidden asymmetries mathematically.
It is. Sectional curvature, at its essence, measures how much paths diverge or converge within a specific plane of a higher dimensional space. In our context, it reveals how much the direction of problem transformation might be inherently different from its inverse.
Showing those hidden asymmetries.
Exactly, those deviations that lead to non-reversibility. It's a deep mathematical idea now being applied to the abstract space of problems, giving us a quantitative way to grasp these intuitive frustrations we sometimes feel when solving complex problems.
So this measured curvature, this inherent twist in the problem space, leads to some truly interesting and often frustrating consequences, especially around the idea of irreversibility. It's not just theoretical, is it?
Absolutely not. It's very practical.
No.
If the problem space is truly curved, then transforming problem A to problem B isn't simply the inverse operation of transforming B back to A.
Right.
The forward path, say A to B, might be relatively easy or efficient, while the backward path, B back to A, could be considerably harder, more resource-intensive, or, crucially, lossy.
Meaning you can't recover all the original information? Exactly.
It's like walking forward and then just perfectly reversing your steps isn't possible. There's an inherent asymmetry, a one-way street quality to certain transformations. I think we've all experienced this. You can break an egg and cook it, but you can't exactly uncook it back into a perfect raw egg. The process is fundamentally irreversible.
That's a perfect intuitive example of what mathematicians call a non-involutive process, a function that isn't its own inverse. Think about a cooking recipe. It's a clear process from raw ingredients, problem A, to a cooked meal, problem B.
Okay.
But try to perfectly reverse that cooked meal back into its original pristine raw ingredients. You can't. You can try to separate components, but you'll have lost the original form, energy, maybe even some mass.
The structure is gone.
Given all this, how do humans, and perhaps even more fascinatingly, increasingly sophisticated AI systems manage to solve problems so much faster sometimes? How do we find what seem like magical shortcuts through this complex, twisted landscape?
Yeah, it seems counterintuitive, right? The profound answer lies in something called inductive bias.
Inductive bias, okay.
It's our prior knowledge, our inherent assumptions, or even just our learned preferences that effectively warp or bend this problem space to our advantage. We don't just stumble through blindly. We inherently guide our search.
And we do by making educated guesses based on past experience or built-in assumptions.
This is where the lensing metaphor comes in, right? Like gravitational lensing in physics.
Exactly. It's a direct and powerful parallel. In physics, a massive object, say a galaxy, curves space-time around it. This curvature causes light rays from distant sources behind the galaxy to bend as they pass by.
And reach us, sometimes magnified or along paths we wouldn't expect.
Precisely. Similarly, our prior knowledge, our inductive bias, effectively curves the problem space. Instead of blindly hiking every single possible path in this complex landscape, our search trajectories bend, gravitationally drawn towards the most promising regions.
So it effectively shortens the perceived distance to good solutions.
Yes. It's like adding a significant mass to the computational landscape, producing what we can call geometric lensing that funnels our effort along demonstrably lower-cost paths. This is how we in AI models get what often looks like a free lunch.
And this isn't just a metaphor. It has a formal echo in the language of curvature we were talking about.
It absolutely does.
Yeah.
In our mathematical notation of curvature, a completely uniform distribution of problems or possibilities where anything is equally likely would have zero curvature. It's a flat, unbiased landscape.
Right.
But the moment you introduce a biased prior our human insight, our knowledge that some outcomes are more likely than others, you effectively introduce a lens mass term. This mass makes formally flat cycles shrink or stretch, depending on how that prior densifies or makes certain regions more prominent.
So the prior knowledge is the mass creating the curve.
That mass term is precisely the statistical structure that humans have discovered over millennia and are now encoding into our problem-solving algorithms.
Let's see this lensing in action. You used a great cricket example in the notes. Let's walk through that. Imagine you're trying to predict which of three batsmen, Ankit, Bhavesh, or Chirag, will top score in an upcoming cricket match.
Okay.
Every probe you make watching highlights asking a coach costs you time.
Right. First, let's consider a scenario where you operate under a uniform prior. No inductive bias. You have zero inside info, so rationally, each batsman is equally likely to top score.
1/3 chance each. Flat landscape.
Exactly. If you have to find the top scorer and can only probe one at a time, you might probe Ankit first. If not him, then Bhavesh. If not him, it must be Chirag.
So on average, how many probes would that take?
Well, there's a 13 chance you get it on the first probe, a 13 chance on the second, and a 13 chance on the third. The average is 113 plus 213 plus 313 plus 63 equals 2 probes. An unbiased methodical search averages 2 probes.
Okay, 2 probes on average with no prior knowledge. But now let's introduce a biased prior knowledge. Let's apply some powerful lensing by form. You've been following the recent games, and you know Chirag is on fire, scored 80 not out, 95 not out in his last 2 games.
He's in great form. That's strong evidence.
So your prior belief, based on this strong evidence, is that he's, say, 60% likely to top score, while Ankit and Bhavesh are each only 20% likely. This is your lens, your bias.
Now, your strategy changes entirely. You'd be smart to probe Chirag first.
Makes sense. Go with the highest probability.
If he is indeed the top scorer, 50% chance, you're done in just one probe. If not, 40% chance, you then have to probe one of the others. Let's say you probe Ankit next.
So what's the average number of probes now with this bias?
Let's calculate. There's a 0.6 chance you need one probe, Chirag. There's a 0.2 chance Chirag fails, but Ankit succeeds. 2 probes. There's a 0.2 chance both Chirag and Ankit fail, meaning it must be Bhavesh, 3 probes. So the expected number is 1.6 plus 2.2 plus 3.2 equals plus 0.4 plus 0.6 plus 1.6, 1.6 probes.
1.6 probes. That's down from 2.0 probes. You save 0.4 probes on average.
Exactly. That 0.4 probe gain is your free lunch. It's a genuine shortcut.
And this is the key point. It only exists because you prepaid for it with insight into Chirag's form.
Absolutely. Without that knowledge, without that prior, the pitch would be flat again, the probabilities would be 13 each, and every opener would demand equal scouting time, forcing you back to the 2-probe average.
So the free lunch isn't really free, it's just paid for upfront with knowledge or assumptions.
This is the very essence of inductive bias in action, and it's a foundational concept in machine learning and artificial intelligence. It's often referred to as the secret sauce that lets models generalize beyond their training data and make sense of the complex, messy world.
So let's get specific. What exactly is inductive bias in machine learning formally?
At its core, inductive bias is the set of assumptions, preferences, or constraints that a learning algorithm makes to generalize from the limited, observed training data it sees to unseen real-world test data it hasn't seen.
Why is it so absolutely necessary for any learning system? Why can't it just learn from the data alone?
Because the data alone is almost always insufficient. Imagine an algorithm trying to learn a pattern from just a few examples. Without bias, it would have an infinite number of ways to explain that data, most of them completely nonsensical or overly complex.
So it needs guidance.
Exactly. Inductive bias is what helps it choose a reasonable hypothesis, a reasonable pattern among the infinite possibilities. It's how an algorithm decides which patterns to prioritize, which relationships are more likely to be true in the real world. It helps us avoid two common pitfalls.
Underfitting and overfitting.
Precisely. Underfitting happens when you have too weak or too restrictive a bias. The model is too simple, misses important patterns in the data, and performs poorly even on the data it was trained on. Overfitting. Conversely, this occurs when you have too strong or maybe just a mismatched bias. The model becomes too complex, memorizing the noise and peculiarities of the training data rather than learning generalizable patterns. It performs brilliantly on what it's seen, but fails miserably on new data.
So inductive bias is that critical bridge from finite examples to infinite real-world scenarios.
Perfectly put.
And what are some different categories or types of inductive bias that algorithms employ?
Broadly, we can think of a couple of types. There are restrictive biases, which essentially rule out entire classes of functions or hypotheses from consideration altogether.
Like using a linear model.
Exactly. If you choose a linear model, you are inherently assuming that the relationship between your inputs and outputs is linear, thus restricting the function space you're searching in. You've excluded all nonlinear functions from the start.
Okay, what else?
Then there are preferential biases. These don't necessarily exclude hypotheses entirely, but rather rank them, favoring certain types over others. Often, they favor simpler, smoother, or more plausible ones.
Like Occam's razor.
Very much like an algorithmic embodiment of Occam's razor. The principle that the simplest explanation that fits the data is usually the best. We also see biases like maximum likelihood, favoring models that make the observed data most probable, or maximum a posteriori, incorporating prior beliefs about the parameters.
And this brings us beautifully, I think, to a foundational concept in optimization and machine learning, one that often gets misunderstood. The famous, or perhaps infamous, no free lunch theorem.
Ah, yes, the NFL theorem.
It seems to fly in the face of what we just discussed about finding shortcuts and leveraging bias. How does it fit in?
It does seem contradictory at first glance. The no free lunch NFL theorem states very precisely that averaged over all possible problems or all possible objective functions, no single algorithm performs better than any other. They all yield the exact same average performance.
So this is the flatland scenario you mentioned earlier, right? A completely uniform, unbiased problem space with no structure, no lensing.
Precisely. Imagine a perfectly flat, uniform problem space where you have absolutely no prior knowledge about the structure of the problems you're trying to solve. In that scenario, every path, every algorithmic strategy is equally good or equally bad on average.
No inherent shortcuts to exploit?
Because, by definition of all possible problems averaged together, there is no inherent structure to exploit overall. For any two algorithms you compare, A and B, there will be just as many problems where A beats B as there are problems where B beats A. It's a completely level playing field where no one gets an inherent advantage without bringing some external information or bias.
So how does this link back directly to our discussion of curvature? Where does the NFL theorem fit into this geometric view?
The connection is fundamental. The NFL theorem holds true specifically under a flat or uniform prior distribution on all possible objective functions or problem instances.
Flat prior means flat space.
Exactly. This flatness in the problem distribution directly corresponds to zero curvature in the hypothesis space. No preferred direction, no structure. When there's no inherent structure, no curvature in the overall problem set you're averaging over, no algorithm can exploit hidden patterns, simply because there aren't any on average. Every probing schedule, every algorithmic approach yields the same total reward or the same average performance. It powerfully reinforces that any perceived free lunch must come from somewhere other than the algorithm itself. It must come from the problem distribution not being uniform.
Okay. Let's delve into how this applies to those NP hard problems we mentioned, the really tough ones. How does the no free lunch principle show up in their time compute scaling laws?
Right. For NP hard problems, we know the intrinsic amount of work required to find a solution generally grows exponentially with the size n of the problem. Let's say the cost is roughly E alpha, where alpha reflects the difficulty.
Okay, exponential growth. Hard.
Now, if you give an algorithm k units of compute power, say k times the processing speed of a baseline machine, How does the time change?
So if I double my compute power, going from K to 2K
You
units,
just have the time.
look,
GKS.
just have the time. That's only a linear speedup. It helps, but it's not fundamentally changing the exponential nature of the problem.
Precisely. This linear speedup contrasts starkly with what one might ideally hope for, maybe an exponential speedup where doubling compute power cuts the time much more dramatically. But for NP hard problems, the standard models suggest you only get this linear improvement. Even astronomically large increases in compute power still leave you largely battling the fundamental exponential complexity.
It's a fundamental limitation, not a path to easy solutions. And this relates back to compute curvature.
Yes, we can define a kind of compute curvature that compares the actual time scaling to an ideal scenario. One way to look at it involves comparing the actual time reduction to what you'd get if compute power scaled perfectly. A formula derived in the sources, related to the one you mentioned earlier but focused on compute scaling, suggests related to kappa. For NP-hard problem scaling is alpha k. This effective compute curvature calculation turns out to be always positive for any practical compute increase.
Kappa 1. Always positive kappa in this context. What does that mean?
What this positive kappa signifies here is a strong irreversibility or resistance in the time compute trade-off for NP-hard tasks. It means that even if you throw astronomically large amounts of compute power, increasing k at these problems, you cannot overcome their inherent exponential complexity beyond that constant linear factor per doubling of resources.
It's like the problem space itself pushes back against being solved faster just by adding more raw power.
That's a great way to put it. It's another manifestation of the no free lunch principle, applied specifically to the time-compute relationship. Think of it like trying to compress an incompressible file. You can use a faster processor, but you can't make the file fundamentally smaller beyond a certain point. The positive compute curvature signals that the problem's inherent difficulty, its exponential nature, resists your efforts to flatten it completely just by adding more compute. The difficulty is baked into the problem's geometry.
So, to tie this all together beautifully, when an algorithm appears to gain a free lunch, performing exceptionally well on a specific problem, seemingly effortlessly, it's truly an illusion.
It is. The lunch was, in essence, prepaid.
And that prepayment comes from human ingenuity, right?
Precisely. Humans invest immense cognitive and empirical work to discover structure in real-world data. We observe patterns in nature, develop grammars in language, invent engineering principles, uncover the logical constraints in a puzzle. This isn't trivial. It's a monumental, ongoing scientific and intellectual endeavor.
And this discovered structure, this deep understanding of patterns, leads to what we call a non-uniform prior over problems. Things aren't all equally likely anymore, which, as we've discussed, mathematically translates directly to geometric curvature in the problem space.
Yes. The space gets warped by our knowledge. And then, inductive bias serves as the mechanism to encode this human-discovered structure directly into the algorithm's architecture or its pre-training data.
Making the algorithm aware of the discovered structure.
Exactly. This encoding allows the algorithm to effectively ride that curvature, like downhill skiing on a perfectly groomed slope or navigating a celestial body using gravitational slingshots. The path costs effectively shorten because the algorithm isn't exploring a flat, uniform landscape, but one where the human discovered shortcuts, the biases, are already embedded and exploited. Thinking about it geometrically really changes perspective.
It really does. This has been a truly fascinating and deeply insightful dive into a concept that I think profoundly shifts how we should think about problem solving, how your mind's geometry might actually bend.
That's right. I mean, imagine your mind's problem-solving process. Think of it like a whole universe. How the simple assumptions you make, sort of on the surface, can actually create this complex curved deep space inside your head, a space full of shortcuts. It's definitely inspired by a pretty profound concept in theoretical physics, yeah.
The core idea mirrors something from physics, right? The ADS-CFT correspondence, where you have a flat boundary, no gravity, mapping to a curved, higher dimensional space with gravity. Is that the basic parallel here?
Exactly. That's the foundation.
Wow, okay, that's a powerful idea.
Absolutely. Your inductive bias acts like a gravitational lens. Just like a massive star bends light, your prior knowledge, your assumptions, they bend the search paths you take when problem solving. Think about tackling a complex project, maybe debugging code. Your experience, your bias towards checking certain areas first, that steers you. It helps you bypass dead ends you might have explored otherwise. That's your mental gravitational lens.
A gravitational lens, bending our mental search paths.
Precisely. It's part of why an expert sees solutions, a novice misses.
Okay, so How does this view interact with the no free lunch theorem?
Well, it builds on it, really. The no free lunch there basically says if you have no prior knowledge of perfectly flat boundary, in our analogy, then all problem-solving methods are, on average, equal, no shortcuts. But when you add bias, when you let your assumptions curve the problem space, you inject structure. The curvature is the structure.
Yeah, that's pretty compelling. It's not just abstract, then. It offers a genuinely new lens for thinking about intelligence, bridging physics, math, AI.
Exactly. It suggests cognition isn't just flat computation, like a computer following simple rules. It's more like a dynamic, holographic emergence of structure.
Just to recap some key takeaways for you listening.
First, problem transformations are inherently directional and lossy. They just are. Moving from one problem representation to another, and then back again, inevitably leads to losses in clarity, increases in computational time, or the introduction of approximations in information loss. It's not a perfect two-way street.
Second, this asymmetry in transformations reveals curvature. This fundamental twist in the problem space can be quantitatively measured using a curvature metric, kappa. A non-zero kappa is that fingerprint of hidden complexity, revealing inefficiencies, unexpected path costs, or irreversible qualities in transformation loops.
Third,
Inductive bias acts like a gravitational lens for problem space. Our human insight, our prior knowledge, and the assumptions baked into AI architectures act as a powerful lens.
there are no inherent shortcuts or advantages in a truly uniform, featureless problem space. The lunch is only free if you've already paid for the ingredients and the chef's expertise, so to speak.
Next time you're trying to solve a thorny problem or struggling to reverse a process, remember that you might be operating in a curved space.
Definitely something to mull over.
We'll certainly be thinking about it, and we hope you will too.